In our previous lesson, we looked at theorems and postulates that said if we have parallel lines, then certain relationships exist amongst the angles. In this lesson, we are going to be proving that lines are parallel. And to do this, we are going to use what is called the converse of a theorem. A theorem, as a reminder, is given as an if-then statement. So if we have P, then Q is the result of that action. Well, when we look at a converse, we reverse this. We say if Q, then P. And taking this into account, let's look at the converse of the corresponding angles theorem. The corresponding angles theorem converse states, if a line crosses two others and forms corresponding angles that are congruent, then the two lines are parallel. So now we're starting with the two angles and making the lines parallel. So I start out here with two lines. I place a transversal across them, and through measurement and calculation I find that these two angles are congruent to one another. Well, if those two angles are congruent to one another, then it must needs be that the two lines that were crossed originally are parallel. That's all that we work with when we have this converse theorem idea. So let's take that base idea and expand it a little bit more. If I have lines formed here, call them L and M, with another pair here, we'll call them A and B. Number a series of our angles. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Now what if I told you that I knew that angles 2 and 6 were congruent to one another? Based on that information, which lines would be parallel? Well, according to this converse theorem, if we have this setup, here we have corresponding angles that are congruent. What makes them corresponding is this line M being the transversal. Then lines A and B would be parallel. So we can conclude that A is parallel to B. It's an application of the converse of this theorem. But we also have other theorems that we could take the converse of in order to prove parallel lines. We have Theorem 3.5, which is the converse of the alternate interior angle. Theorem 3.6, converse of the same side interior. And Theorem 3.7, the converse of the alternate exterior. So with these theorems, we're simply going to take our if-then statements from before and trade them. Let's begin with 3.5. If two lines and a transversal form alternate interior angles that are congruent, then the two lines are parallel. Taking the same idea and applying it to the next one, converse the same side interior angle theorem. If two lines and a transversal form same side interior angles that are congruent, then the two lines are parallel. And last, the converse of the alternate exterior angle theorem. If two lines and a transversal form alternate exterior angles that are congruent, then the two lines are parallel. Going with these, we can reverse a lot of the work that we did in the previous lesson and apply the ideas here in the new. So let's take a little look of how we might be able to do that. In this diagram, we have lines A and B with transversal M, and I have two angles marked. What would X have to be to make it so that line A is parallel to line B? Well, using the converse of the alternate interior angles theorem, I can say that in order for those two lines to be parallel, then these have to be congruent. So I'm going to take 4x minus 7 and set it equal to 2x minus 3. Now, plus 3. Now solving for x, I subtract 2x from each side, giving me 2x minus 7 equals 3. Add the 7, 2x equals 10. Dividing by 2, I have x equals 5. So if x is 5, it will make the two angles congruent. Specifically, 2 times 5 plus 3 is 13. 4 times 5 is 20 minus 7, again, is 13. The two angles would be 13 degrees each, and because they are congruent, the lines must be parallel. So the ideas that we cover here are real short and simple, just working off the ideas that we already have. Make sure you have these ones down, because we're going to be using them as we move forward in our discussions about parallel and perpendicular lines.